So back to number 4, world record running up the stairs, Empire State Building, 8 minutes. That's fake news. That's not real. It's actually like 9 minutes. I don't know where I got this from. I don't remember. Total height change around the stairs is 380 meters. The record holder has a mass of approximately 70 kilograms at the time of the challenge. Why don't we change it right now to the 9 point? I don't know. Re-upload this. What? 9.3 minutes.
10 minutes.
9.33. 9.3 minutes. The total height change in running upstairs 300 meters record holder. Okay. Determine the record holder's average power output.
It would be 9.5.
Yeah, power equals change in energy over time. All right. Change in energy is, in this case, change in gravitational energy is what we're going to study. So if you did the lab last year running up the stairs, I think our top horsepower is usually around 2 horsepower. That's a really strong horsepower. You got to have a pretty decent amount of mass to be able to get a high horsepower rating running up the stairs.
How much horsepower does one horse have?
All right. Change in energy,
It's obviously more than one.
You can put a delta in front of the H if you wish. You don't really need to. So the power here is 70 kilograms times 9.8 newtons per kilogram, or I guess we can just use 10 newtons per kilogram. Times the change in height, 380 meters. Time has to be in seconds when you calculate power. Time always has to be in seconds. So 9.3 minutes times 60 seconds per minute. All right, so the minutes are going to cancel. We're going to end up with units of joules per second. Joules per second. So 70 times 10 times 380 divided by 9.3 times 60. All right, 476 watts. Which is quite a bit less than what we generated running up the stairs in the back hallway. But one of the questions we talked about in that lab last year was, okay, what would happen if the flight to stairs were way longer? The endurance person is going to end up with the higher power. Like some people, actually, this would be a pretty low horsepower rating for the lab we do up the stairs. You guys did that in Strickland's run up the stairs? Mm-hmm. Yeah, I want to say you're generating closer to like 1,000 watts running up those stairs. So, yeah, so that's really not that crazy on paper, but it's the endurance factor that, you know, if we try to do this, we'd be like 50 watts. All right, so number 5. This is an interesting question. It brings in the concept of work, which we haven't talked a whole lot about. It did show up in that video. We're going to kind of tie it together here, okay? Let's go ahead and read the question and try to visualize this. A 2 kilogram remote control tank consumes 150 joules of electrical energy. So let's say the battery has a capacity of so many milliamp hours, which is directly convertible to joules of energy. So when you see the milliamp hour rating of a battery, rechargeable battery, that's how long it will last for at a certain current draw for a certain amount. So the less current you draw from it, the longer it will last. So you could figure out what the energy capacity of that battery is. And then you figure out things like energy density. Maybe you've heard of that with batteries before, their energy density. You know, LiPos are the really good ones. Those little batteries, you know, they're these little, you know, they're like blue, usually blue heat shrink covered. They're very energy dense. Anyhow, so the question is, let's say it gets up to a speed of 5 meters per second. How much has the internal energy of the system increased? So you're putting in 150 joules and you're getting up to a certain kinetic energy. So for this one, you have to start by figuring out what that kinetic energy is. So you're using an electric potential energy of 150 joules. All right, let's figure out how much work is actually done overall here. Now, here we go. The net work done on an object is always equal to the overall change in kinetic energy. Alright? It's always equal to the overall change in kinetic energy. This is called the work energy theory. Alright, I'm not even bringing in force and distance at this point. This is just a big concept that the net work done on an object can be determined by determining its speed and mass, knowing its mass and determining its speed. Figure out its kinetic energy. So, at the end of the day, this object here, right, this would be KE final minus KE initial. Usually KE initial is just 0. So the work net ends up being equal to 1/2 of 2.0 kilograms times 5 meters per second squared. So that's only 25 joules of kinetic energy that it ended up with. 25 joules of kinetic energy it ended up with here. That's not great, right? We put in 150 joules of electrical energy to this system. However, we only end up with 25 joules of kinetic energy. What? That stinks. Well, the rest of it, went into thermal energy, basically. Think about a tank, a tank, if it's treads, it's going to cause roughing up the ground. It's a toy, how much is it going to rough up the ground, but there's a lot of material in contact there. It's not very efficient. The heat of the battery, the electric motor, if it's a remote control, you power in the speed control, you power in the receiver, all that other stuff is dissipating that electrical energy. At the end of the day, you're only getting out 25 joules of kinetic. So, U internal must have been, so think about the bar graphs, right? If you're to make bar graphs for this, right? Here's the tank, right? Here's the tank, starts off at rest, and then tank is moving. Well, basically we have U electric, kind of like other energy source, right? So it's all electric potential energy to start off with. Once it's moving, maybe we haven't totally zapped the battery, right? Maybe I've decreased by 150. Well, that 150 is going into electric, kinetic, U internal. Only a tiny portion of it's gone into kinetic. That must mean whatever's missing of those two has gone into internal. So that's got to be the 150 minus the 25. That's got to be 125 joules. So the internal energy built up here is 125 joules. All right, it's the missing component. Now, part B. And the first time I tried this video, this is what I messed up. If we think about the forces at play here, right? Is there any one singular force that friction, drag, and everything is applying? Is there just one singular force? Definitely not. It's very complex, right? There's a whole bunch of stuff happening here. So part B is a little bit of an artificial question, right? It's not some magic singular force that's causing the battery, the motor, all that loss, right? But what we do here is we kind of pretend there is a singular force. If it was a simpler problem, like a frictionless cart with a sail or something, like a Rolls frictionless has a sail, that would be a single force that would, take away energy into air drag and such. Now this one's not so simple. So the one thing we talk about is work net equals change in kinetic energy. You can also determine that by doing F net, but it's got to be the net force parallel to the displacement. All right. This I talked about in the video with the dot product and parallel component and different things, and it's a little confusing. We're gonna build that up later on. But work can be force times distance, basically, right? So the work done by the friction, so to speak, the lost energy, all right, it's actually going to be the force of friction times the displacement, right? Individual forces do work, and if you add up all those individual forces works, it ends up being equal to the total work done, or the total change in energy. So for part B, we're just being asked about the frictional force. That's what's causing the internal energy buildup, right? So this is just 125 joules equals the force of friction. Again, force of friction is very artificial in this, at 4 meters. 125 divided by 4 is like 60 something, right? Or no, 20 something. Was it? 31. Jeez. So the force of friction overall, if it was a singular force, would be 31 newtons, and that's not really. You know, it's like there's no singular force causing this energy buildup. It's actually pretty complicated. All right, now the last thing here, the video, I just want to go over the setup of it right now. And I really want you guys to really try this one on your own, okay? I'm going to check to see that you did number 6 next time I see you guys, okay? I'm going to check to make sure you gave this one a shot. Now there's one thing I need you to change in the diagram. That 0.1 meters should not be on the 0.1 meters should not be on the last card position. It should be on the middle card position. And I fixed it in the file that I posted, which I'm going to change again and repost to the Empire State Building question. I fixed it in that file, but I already copied these and didn't want to waste paper, so I just figured I would fix this for you here. So what we have is a cart being launched up an incline by a spring. And I asked you for the speed of the cart when it's 1.10 meters off the ground. So I asked you for the speed of it when it's that high off the ground. That should be pretty straightforward, right? Because it's going to be kinetic energy here, or sorry, PS here, not EPS, US, UG, K, right? So the offspring energy start off. All right? Then here, right, what's it going to be? What's going to be there?
Gravitational potential and kinetic.
Yep. And maybe it's 50-50. Hard to say. Right? Hard to say. Who knows? And at the top, what do we have at the top? When it stops and is about to roll back down. What do we have at the top there?
All potential, no brakes.
All potential, no brakes. Yep, it's going to roll up
All hunter,
and
no
come
body.
back down. Hit the spring again. And in a perfectly closed system, when it hits that spring, it's going to compress it the same amount it was compressed initially, which is kind of cool. But anyway, so part A is determine the velocity of the cart when its height is 0.1 meters. So that's when it's here. So the arrow in the diagram should be shifted over there. I tell you the incline here. And that's a distractor initially. Kids will start drawing force diagrams and, you know, because you see that incline and the angle, your brain instantly thinks like, oh, wait a minute, I got to do that weird force diagram with that. You're not going to need to do that, okay? You're not going to need to do that. So what it's asking in part B is, how far parallel up the ramp will the cart go until it comes to rest and starts to roll back down? So what you're actually looking for is this distance, right? That's the distance I'm looking for. You can't directly calculate that. You could actually, if you determine the acceleration parallel to the ramp and the initial velocity of the car when it leaves the spring, and blah, 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 blah. You could do that directly. Really what you need to do is figure out this height, right? Figure out this height final or height max, I guess you would say. You need to figure out the maximum height and then use the geometry of this triangle to figure out D. Which, first time students see this, if I just throw this on a quiz, this is thrown at you in an AP exam, like nobody recognizes to do that. Even though it's not that hard mathematically, it's one of those things that you have to recognize to actually do it, you know? But, anyhow, there it is. I want you to figure out the rest of that problem. We'll go over it in class. I'll write these solutions up. I'll fix that one problem and repost it. I think we're good to go.